Hello everyone. So we are back. We are doing plasma applications. Now in this class, we will be addressing three very interesting applications. One is atmospheric pressure plasma spray, APS usually it is called. Then we will see application of plasma in plasma metallurgy, and then we will see how we can use this plasma for noble material synthesis. So, we start with atmospheric pressure plasma spray. As the name suggests that APS is done at atmospheric pressure. So, the moment you say that you are doing a coating at atmospheric pressure, then those who are familiar in this area, they will immediately say it has great advantage that you don't need a vacuum system, because any coating that you require vacuum, so there the deposition efficiency becomes less, because anyway the number density of the particles are there less, and the other thing is that you need to create a vacuum. So that vacuum creation and maintenance of that vacuum at certain standard level is not a simple thing. So what you are seeing here at the bottom, the plasma spraying process, this is actual spraying as it goes on. A plasma jet is coming out from the torch, then you are feeding some powder in this jet from somewhere, and then that powder is coming, getting melt over here, and then getting deposited over the substance you want to coat. Now, if you want to melt some material, then why the plasma jet is required? This is mainly because the kind of material you are going to spray over here, they are high temperature refractory materials. Usually they are like that because they are because of their very high melting point and the necessity that you instantaneously melt them and flow them out to get deposited over a surface before they cool down, you require the very high temperature jet of the plasma. By no other means you can melt a ceramic say material like yttrium oxide, aluminum oxide, which are having extremely high melting point. You cannot melt them instantaneously and spray them over the substrate that you want to coat with. So you are seeing here the actual spray process as it is going on. You require a robot which will precisely do the job. You can program the robot in a way that it covers the area of your interest, and typical peripherals for plasma spray system are shown schematically over here. So this is the plasma torch. Of course, nothing in this are as per scale, because plasma torch is actually a very small object here, and these are the cylinders are of your height, and computers how they are, but here the plasma torch is shown, the most prominent one in this schematic. So you don't go for scaling, only for understanding purpose this has been drawn. So apart from the plasma torch, you need a chiller system which will cool the highly stressed components. Now, apart from the cooling, you need a gas supply system like this one. Then for the plasma torch to operate, you need a power supply. Then there is a powder feeder unit which feeds the powder at a certain rate decided by you to the plasma jet. Then you have a robotics which actually moves this plasma jet as you are seeing over here over the substrate to be coated. So I come to the application areas of APS coating. The aerospace is one of the area where turbine blades, combustion chambers are getting coated for thermal barrier coating. In the biomedical area, implants like hydroxyapatite coatings are used. In the energy sector, fuel cells, gas turbines, they use these APS coatings. In the automotive area, engine components to which are undergoing a very high friction, so they are basically coated with this material, so that that even though they are the one surface rubs over the other surface, their life can get elongated. Now in the electronics, dielectrics and conductive layers are formed using the APS technique. What are the benefits? Good bond strength, high temperature resistance, wear and corrosion protection, and customizable coating thickness and composition. So they are the benefits, and here I should like to mention that the kind of thickness you get over here, it can easily extend from 100 micron to even 1 millimeter using this technique, which is no way possible using low pressure deposition like PVD-CVD method. So that is one of the major advantage of APS coating. Of course, there are disadvantages. So APS coatings are prone to porosity. So there are pores inside this coating because they form by layer development, and between two interlayers there may be pores. The good part is that those pores are, most of the cases, they are blind pores, so they are not open at the both ends, so they can protect the substrate from the environment very well. There is no issue in that. And sometimes in cases where thermal expansion is concerned, these pores actually helps. Like there are two rails, when you feed them, you put a gap. Because of what? Because when they expand, when the train travels through that, the wheels move on that, they heat it, so through that heat it can expand, and that gap is there to accommodate that expansion. So in similar cases, if there is no pore, in some cases the material may break when such expansion are there. But if there are pores that can absorb that expansion, and it can give a better mechanical suitability. So those are there. And then what do you call the adhesion? So you get a very good adhesion in this case. And coating materials, what you use for? They are basically ceramics most of the time, because they are, you require very high temperature material, and environmental barrier coating. So use oxides of metals like aluminum oxide, yttrium oxide, neodymium oxide, and sometimes this yttria stabilized zirconia. This is a very common material which is used for such coating. Then metals and alloys, MCRALY. M stand for the metal. Sometimes M is nickel, and that NiCrLy is quite often used in this coating area. Then carbides, carbides are known for their very high mechanical strength. They are very hard material, these carbides. So tungsten carbide, they are many times used for coating, and especially because of their very high melting point, this plasma is the only suitable method to melt and spray and develop coating. Then one thing I should like to draw your attention, that the interlayers sometimes are required between the main coating and the substrate. You may require an interlayer to match the thermal expansion coefficient. So the binder and the particle size is very much important, because if you have a thicker particle, they may melt on the surface because this is instantaneous melting, and they may even stay hard at the core. They are not in molten state. So the particle size you should choose very properly. Usually 40 to 60 micron particle size are good enough for flowability as well as for melting, complete melting. Okay. So you need to make the powder flowable in the carrier gas so that they can enter into the plasma, and at the same time they should be completely melt during the dwell time of those particles inside the plasma, so that when they flow out in molten state and they can deposit on the substrate. Now to just make you familiar with what an actual plasma spray coating setup looks. So this is one acoustic chamber we call, because the plasma that emits UV radiation, that plasma torch gives too much of noise, and then the hazardous gases are produced inside, which is not good for your health. So what you do, you should do everything inside a chamber that is called acoustic chamber, because the sound that doesn't come out from there. So this is basically a room inside room. Inside that there is an evacuation system, there is a filtration system which sucks out whatever the gas that is getting generated over here and release it to after proper filtering, they release it to the atmosphere. And then what here you are seeing inside is expanded little bit here. So this is a robot which is programmable at the console that is over here. So you can program the robot to move in a proper manner so that it can coat the the portions of interest of your object which needs to be coated. So you can precisely program over here, you can control your plasma torch operation, decide the parameters in this console, control console, and this one is the powder feeder unit which feeds the powder to the plasma jet, that is over here. Okay. So this requires this power supply unit, there is a chiller unit which is not shown here. So all this together basically form the plasma spray setup. Now after the coating is developed, you need to characterize them for their adhesion test, for their microstructure. So you need all this a diagnostic and testing setup for qualifying the coating that you have developed. So what is the thickness, what is the microstructure, what is the adhesion strength, so all these things you need to know. Now different coatings, how they look, I just show at the bottom. This is a graphite crucible, you can see the color, you can understand this is made, this is a graphite crucible. When it is coated with yttria, it looks like this. So yttrium oxide is pretty good white, and that color is seen on this thing. Similarly, we can we can develop coating of any material. Here you are seeing some material like copper, nickel, tantalum, SS. Then on molybdenum, these are the showing the yttrium coating developed. And other very interesting thing is that you can develop metal coating over metals. So here copper on copper we have developed, and Ti2 on copper is over here. Then alumina coating is another refractory metal. So extremely high enthalpy of thermal plasma jet greater than 10,000 degree Kelvin is used for instantaneous melting and coating of high temperature materials, alloys and composite and ceramics to provide thermal barrier, wear resistant or corrosion resistant coating. So adhesion strength over the material you can easily get more than 10 megapascal. It is very common between common and between the substrate and the coating. So that is why it is very useful area, and the reason why they are useful I have already told you over here in this slide. Now I will come to the other application area which I promised. This is called plasma metallurgy. Now you know that plasma metallurgy is a high temperature extractive metallurgy technique that uses thermal plasma to process ores, refine materials or synthesize materials. Plasma, the thermal plasma is known for its very high gas temperature. So extremely high temperature 5,000 to 20,000 degrees centigrade it can easily achieve. It uses ionized gas as heat source. It can treat refractory and complex ores. Extraction of titanium, chromium and rare earth metals are very common using this technology. Refinement of steel and aluminium, they are in practice. Waste treatment and metal recycling are a very common practice in this area. Then fast reaction rates that you can get through the presence of these reactive agents like nascent atoms and ions. Then energy efficient high temperature process is possible because of presence of this nascent species. Then the most important thing is that it is environmentally benign process because of the very low discharge of the harmful substances. But the cons of this, these are all pros of whatever I have told you, but there are certain drawbacks of this method. So what is the one? At the first place is the capex, the capital expenditure that you do to install such systems. You really need high investment. For example, if you want to put a precise robot which can make a move of say 0.1 millimeter kind of thing, that is really costly. Then plasma power supplies, then all the post processing system, and the plasma diagnostic system and qualification of the coating, the instruments that you require. All these things make a complete setup, and the capital expenditure that you go for initially is really high. And of course, because plasma you require a skilled technician to operate, so that also adds to your cost. So these are some of the drawback, but this is the only process by which you can very efficiently coat very high temperature refractory ceramic materials for many very interesting and important applications. Now I come to the plasma metallurgy, where common effluent treatment plants, the discharge from them are getting treated. So in this you have seen what empowers the plasma to do the extractive metallurgy in so efficient manner. Now when you are doing that, you are getting some benefits which is not possible otherwise. It has some unique aspects that is purely due to the very high temperature of the plasma and because of the nascent species that is being generated over there. And generating such high temperature by other means is really difficult. Now I am showing you one example where this technology is being used, and you are able to extract the material that is there within. Not only you are doing that, you are getting rid of the some substance which are otherwise hazardous. So here what I am showing you here, in the industrial area, the effluent treatment plants, ETP, there is everywhere you will see that there is common effluent treatment plant. Why it is common? Because many industries are allowing their discharge to get commonly collected at certain facility. So that is why it is called common effluent treatment plant. So effluent from many industries coming together. So now three types of sludges are basically produced in this area. One is called polymeric flocculant sludge, PFS. One is called decanter sludge, DCS, and another is spray dryer sludge. So these are three different types of specific types of sludge that are generated in the common effluent treatment plant. And here you are seeing that a thermal plasma jet is impinging on that, and they are processing the material. We have done two trials at different time, and you see that their outcomes are more or less same. You see that here once you expose that to plasma, the volatile component goes away. The volatile component may be from organic or some other substances. Then what is remaining there? Inorganic component and the metallic components. You see that metallic component join together and form a bulk substance, and the inorganic component, they are completely separate from the metallic component. So what we are able to do, you get rid of the sludge that is very difficult to manage. At the same time, you are reducing the volume of the sludge, and what you are doing, you are extracting the useful material from that. Now I move to another very important plasma application area, which is noble material synthesis. Now I'll be basically telling you one example where this is very useful. Now ceramic nanoparticles, they are often different from their bulk counterpart. Why? Because they can give you enhanced emission lifetime, improved luminescent properties, better solid state reaction, better quantum efficiency, better mechanical strength, attractive optical nonlinearity, improved catalytic activity, inherent refractory nature, and better thermal properties. These ceramic nanoparticles can be can give you these attributes. But how to get the ceramic nanoparticles? Because uh, they are having very high temperatures. There are chemical route, wet chemical route through which you can generate that, but there uh, you cannot extend those processes for every material, and the control over the size distribution and the properties may be much better when you are going for these plasma processes. So one of the interesting application is that this ceramic lasers, ceramic Nd:YAG lasers. So Nd:YAG lasers are known to everybody because they are very common lasers used in the lab. Now when you want to go for very high power, like those in the inertial confinement fusion plasmas, so this is another area where thermal plasma is basically contributing in the fusion plasma area. So thermal plasma technology is being used to produce the Nd:YAG ceramic Nd:YAG lasers. Okay, basically this is a Nd is the lasing media and YAG is the host. So this Nd:YAG is the laser rod that can be grown naturally or it can be grown in the ceramic way. But if you are going for very high power, the naturally grown Nd:YAG crystals, it is not possible because you have some limitation and practically they are not doable. So if you want to go for very high power lasers, you need to go for some other route apart from the your natural route. So I come to that. This potential of ceramic YAG is that it can offer high thermal shock resistance, low residual and thermal beam distortion, small nonlinear index coefficients, low susceptibility to laser damage, higher ND doping. That is another very important, because doping of ND, the lasing material, is around 1% or less than 1% in case of your natural crystals. But here in case of ceramic, you can control the this ND concentration to a much higher level. So although the ceramic rods are not as good as the natural grown rods, they can compensate that by enhancing the ND doping. Now, so hence good absorption of available diode pump light near infrared and a reasonable emission cross section for efficient extraction in few passes. This high fluorescent lifetime, then ability to fabricate composite or even continuously graded doping in these materials, it is possible, which is very difficult in naturally grown crystals. This could be used to achieve a desired beam profile and properties and impurities less than 1 ppm. So manufacturing of large scale gain media is possible if you are going through the ceramic route. And you see here the Nd:YAG single crystal and Nd:YAG ceramics, they have been doped like this. This NdYV04 single crystal, their ND doping is 1.1%, Nd:YAG single crystal is 1.0% ND doping, and Nd:YAG you can go up to say 4.8%. So this is a so fourfold, more than fourfold increase. And if you go for the other properties like cross section of stimulated emission, then you see that they are having higher NDY VO4 is quite high, 20, and YAG and ceramic they are nearly same. Fluorescence lifetime, they are these two are comparable, but NDY is quite high. Absorption coefficient here, this is so high because of the presence of the ND. And thermal conductivity here, they are this is quite comparable to this one, but it is higher than this NdYVO4. So now the things remain that how to make this composite. So what we do actually, we take yttrium oxide, aluminum oxide and neodymium oxide, micron size particles. Then we feed that because you need optical grade quality, so you must avoid the impurities by all means. So you are using a electroless discharge kind of thing, this radio frequency plasma, thermal plasma. So you feed your powder to the top and they get evaporated, then through homogeneous nucleation at the bottom side they produce the nanoparticles. Once you get the nanoparticles of yttrium oxide, aluminum oxide and neodymium oxide, then you mix in the stoichiometric ratio and sinter and get your ceramic rod done. So you are using a thermal plasma technology to produce the nanoparticles, and therefore you are forming the ceramic that you want with the desired ND doping. So this is a very interesting and useful application, and you see the application area, it is in the inertial fusion application area, a very important futuristic activity. Now here you see that how it is being done. So this is the plasma that you have seen over there, and here the particles, micron sized particles are fed, and they are then evaporated and in atomic and ionic states. Then they, as they come downstream, they do go through the homogeneous nucleation, and they from the particles, those particles are deposited in the wall, and that you collect, and the structure that you have is here, you see here. So this is 50 micron, this bar what you are seeing over here is 50 micron, 50 nanometer, sorry, 50 nanometer, and so you can understand how their crystalline structure is very obvious over here, and the typical size distribution that you get, it is like this. So you have a peak over here at around 20 nanometer. Now when you sinter, you see that you get a perfect YAG out of those synthesized nanoparticle using thermal plasma. So every peak whatever you are seeing here through XRD, they correspond to the YAG peak. So this has been obtained through sintering at 1800 Kelvin. So now I come to the next application area of this plasma, but this one is application of cold plasma. This is an emerging technology in the area of non-thermal plasma application of in medical technology. So an emerging non-thermal medical technology area is this plasma medicine. So I'll start my class with this one in the next class, and then I will show you the application of thermal plasma in the area of agriculture. So in the next class I will be addressing two things, one is plasma medicine and the other one is plasma in agriculture. So I stop here, I will see you in the next class.